It is the winter of 1942, and somewhere beneath the grey English countryside, in a requisitioned Victorian mansion surrounded by prefabricated huts and the permanent smell of damp paper and cold tea, a young engineer is staring at a wire. Not a long wire, not an impressive wire, just a coil of copper, hand-wound around a wooden former the size of a biscuit tin, connected by soldered joints to a circuit that has been redrawn, rejected, and redrawn again perhaps 40 times over the past 3 months. Outside, the war grinds on. In North Africa, in the Atlantic, in the frozen forests of the Eastern Front, men are dying at a rate that makes the mind go mercifully numb. And here, in this room that smells of solder flux and cigarette smoke, the wire is everything. What the engineer is building does not fire shells. It does not drop bombs. It does not cut through barbed wire or armor plate. What it does when it works, and it is not yet working, is listen. It reaches out invisibly across the electromagnetic spectrum, finds the radio transmissions of the enemy, and rather than merely recording them, it does something far more audacious. It steals the signal. It captures it, processes it, and hands it back to British intelligence officers in a form they can actually use. Not a crude interception, not a raw burst of noise. A clean, intelligible stream of information stripped of the tricks the Germans have built into their communications to keep exactly this from happening. The device will come to be known in the sanitized language of wartime secrecy as a signals exploitation unit. The men who built it will not appear in newspapers. Their names will not be mentioned in dispatches. Some of them will carry their work to the grave, bound by Official Secrets Act declarations that outlasted the war by decades. But what they built in those huts and mansions and converted factory spaces quietly changed the course of the conflict in ways that bullets never could. This is the story of Britain's most secret electronic weapon. To understand why it had to be invented, you need to understand what British intelligence was hearing in 1940 and what it absolutely could not make sense of. Radio communication had been the backbone of modern warfare since the First World War. But by 1939, the German military had done something the Allies had not fully anticipated. They had professionalized it. The Wehrmacht, the Kriegsmarine, and the Luftwaffe each operated extensive radio networks, and those networks were not simply broadcasting in the clear and hoping nobody noticed. They were using layered, sophisticated methods to obscure their transmissions. The most famous of these methods, of course, was the Enigma machine, the electromechanical cipher device that scrambled German messages into apparent gibberish before transmission. Enigma's story has been told at length, and the work at Bletchley Park to crack its codes is rightly celebrated. But Enigma was only the most visible part of a much larger problem. Alongside the enciphered text messages, the Germans were transmitting on a range of frequencies, using a variety of modulation techniques, transmission speeds, and radio fingerprinting methods that made even identifying who was talking to whom an enormous challenge. By 1941, British Signals Intelligence, operating primarily through the Government Code and Cipher School at Bletchley Park in Buckinghamshire, and through a network of intercept stations operated by the War Office, the Admiralty, and the Air Ministry, was collecting enormous volumes of raw radio traffic. The problem was not a shortage of information. The problem was the gap between collection and comprehension. Intercept operators, working in cold huts with headphones clamped over their ears, could hear the transmissions clearly enough. What they struggled to do was capture certain categories of signal cleanly, particularly those broadcast at high speeds, in compressed bursts, or with deliberate frequency variations designed to defeat simple tuning. A skilled German radio operator could transmit a Morse message at speeds exceeding 25 words per minute. Automatic teleprinter systems, like the Lorenz SZ40 used for Hitler's high command communications, operated at speeds no human ear could follow at all. The signal was there. The information it contained was there. But reaching it required something beyond the listening ear and the patient hand of a transcription clerk. The men tasked with solving this problem worked across several overlapping organizations, but the most technically sophisticated of them were concentrated in a section known informally by those who worked within it as the Y Services Dark Corner. Officially, their work fell under the purview of the Radio Security Service, established in 1939 and initially staffed largely by radio amateurs, recruited from the ranks of the Radio Society of Great Britain. These were men who understood the electromagnetic spectrum, not as a theoretical abstraction, but as a landscape they had spent their hobbyist years exploring, mapping, and exploiting for entirely peaceful purposes. What they designed over the course of 1941 and 1942 was a system of considerable elegance. At its heart was the principle of heterodyning, a mixing technique that had been understood in radio engineering since the 1910s, but had never been applied to signals intelligence work with this degree of precision. When a received radio signal is mixed with a locally generated signal of a slightly different frequency, the result is a new signal at the difference frequency, what engineers call the intermediate frequency. This intermediate signal can then be amplified, filtered, and processed with far greater precision than the original, because it sits in a frequency range where the necessary electronic components were, by 1942 standards, both reliable and relatively compact. The British devices being built in this period took this principle and extended it. They were super heterodyne receivers, a design that had existed since the 1920s in domestic wireless sets, but which the signals intelligence engineers had modified almost beyond recognition. The bandwidth could be adjusted with a precision that contemporary commercial receivers could not match. The filtering stages had been redesigned to capture not just the audio content of a transmission, but its timing characteristics, its frequency drift, and its power envelope. The shape of the signal itself as it rose and fell during transmission. This last element was particularly significant. Every radio transmitter has a unique signature. Tiny variations in the way the signal starts and stops, oscillates and stabilizes, that are as individual as a fingerprint. British engineers had realized by 1941 that by capturing this signature alongside the content of a transmission, they could identify specific enemy transmitters, even when the operators changed their frequencies, their call signs, and their cipher keys. The transmitter itself could not hide. The physical devices that resulted from this work were not glamorous. They occupied wooden racks, roughly the size of a wardrobe, filled with glass thermionic valves, capacitors, coils, and the kind of precision resistors that had to be manufactured to tolerances previously considered unnecessary for anything short of laboratory instrumentation. A complete unit weighed somewhere in the region of 60 to 80 kilograms, approximately the weight of a fully equipped infantryman. It required a stable power supply, which in field conditions meant a dedicated generator. It required a skilled operator to tune and maintain it, and it required to be connected to an aerial array that, depending on the target frequencies, might be anything from a simple dipole strung between two trees to an elaborate rhombic antenna occupying an area the size of a football pitch. Production of these units took place at several locations across Britain, most of them converted engineering workshops and light industrial facilities, far enough from major cities to be considered relatively safe from bombing. The workforce included a significant number of women, recruited through the same channels that supplied labor to the wider war industry. The valves, which were the most temperamental component and the most frequently replaced, were sourced from British manufacturers, including Mullard and Marconi Osram, operating at or near full capacity throughout the war. Exact production figures for the signals exploitation variants of these devices remain, even now, incompletely documented in the public record. But estimates drawn from post-war assessments suggest that several hundred complete systems were operational by the middle of 1943. If you are finding this interesting, a quick subscribe helps more than you know. In the field, these devices were deployed in a variety of configurations. In Britain itself, the principal intercept stations at Knockholt in Kent, at Chicksands in Bedfordshire, and at a ring of outstations that stretched from Scotland to the south coast, housed the most sophisticated versions connected to Bletchley Park by dedicated landlines along which the captured signals could be transmitted for analysis. In North Africa, mobile versions of the equipment were carried in lorries, specially modified to provide the necessary power and environmental stability, operating alongside forward signals, units that followed the advance and retreat of the Eighth Army across Libya and Tunisia. At Knockholt, the station most closely associated with the interception of the Lorenz teleprinter traffic that British analysts called FISH. The arrival of improved receiver technology in late 1942 dramatically increased the volume of usable intercepts. Where operators had previously struggled to capture complete transmissions from the high-speed automatic systems, the new equipment allowed recordings to be made on paper tape at speeds sufficient to catch every character. These recordings were then forwarded to Bletchley, where the traffic analysis section would attempt to identify the transmitting station, the receiving station, and the network to which both belonged, all before a single character of the enciphered content had been touched. The psychological impact of this capability on the German signals community, once they became aware, as they eventually did, that their transmitters were being fingerprinted, was considerable. German signals security officers began issuing increasingly desperate instructions to their operators: change frequencies more often, change transmitter settings, vary transmission times, use relay stations to obscure the origin of high-priority messages. Each of these countermeasures cost time, introduced complexity, and degraded the efficiency of the very communication networks the Germans depended upon. The act of listening had become, in its own quiet way, an act of disruption. It is worth pausing here to consider what the Germans themselves had in the equivalent space. The Wehrmacht's signals intelligence service, the Funkerwehr, was technically sophisticated and well-resourced, and German engineers had their own version of the super heterodyne receiver in widespread use. The Telefunkenempfänger E52, introduced in the early years of the war, was a highly capable general-purpose communications receiver with a frequency range covering virtually the entire spectrum in use for military communications. It was well built, well manufactured, and used by both the German signals intelligence services and by Axis allies across Europe. Where the British devices differed was not primarily in the sensitivity of the receiver itself. By 1942, the fundamental physics of superheterodyne design had been well understood by engineers on both sides for 2 decades. But in the systematic integration of the receiver into a larger analytical framework, the British had built not just better receivers, but better systems around those receivers, standardized recording procedures, trained analytical staff, dedicated communication links to central processing facilities, and, crucially, the Hollerith punched card machines at Bletchley that could process traffic analysis data at a speed no human team could approach. The Americans, when they entered the war and began contributing to Allied signals intelligence operations, brought considerable resources and engineering talent. The collaboration between British and American signals intelligence, formalized through a series of agreements beginning in 1943, resulted in the Bruce Agreement, a framework for sharing both raw intercepts and analytical conclusions that represented perhaps the most significant intelligence partnership in the history of warfare. American engineers were, by general assessment, somewhat more advanced in certain aspects of receiver miniaturization, particularly in the development of units suitable for aircraft installation. British engineers, by contrast, had accumulated 2 additional years of operational experience in identifying and exploiting the specific idiosyncrasies of German military communications, a body of knowledge that proved difficult to replicate through technical specification alone. Whether the British approach was superior is perhaps the wrong question. What is clear is that it was different in emphasis, and that those differences reflected the specific operational requirements Britain faced, particularly in the crucial early period when American industrial capacity was not yet available to compensate for analytical shortfalls. The true impact of Britain's signals exploitation capability is genuinely difficult to quantify, and historians have argued about its precise contribution to Allied victory since the first partial disclosures of the ultra-secret in the early 1970s. What can be said with reasonable confidence is this: at several critical junctures in the war, signals intelligence derived from intercepted and processed German communications provided Allied commanders with information that demonstrably altered their decisions. The Battle of the Atlantic provides perhaps the clearest example. In the period between late 1942 and the spring of 1943, as the fortunes of the U-boat campaign shifted decisively in the Allies' favor, the contribution of traffic analysis, which required precisely the kind of signals exploitation equipment described in this documentary, was substantial. By tracking the characteristic signatures of individual U-boat transmitters, analysts could plot the movements of submarines with a precision that pure code breaking alone could not always provide. When an Enigma key was changed and Bletchley's codebreakers fell temporarily blind, traffic analysis continued to yield positional data that allowed convoy routing to continue. The psychological impact extended beyond the enemy. Within British military culture, the existence of a serious, well-resourced signals intelligence capability, one that treated the electromagnetic spectrum as a battlefield in its own right, helped establish a set of institutional habits that would outlast the war considerably. The close relationship between theoretical engineering and operational intelligence the integration of academic scientists into military planning structures, and the culture of systematic analysis, rather than intuitive command, all have roots in the wartime signals intelligence community. Physical survivors of this era are scattered. Knockhold's station, though long since closed to its original purpose, still stands. Bletchley Park itself is now a museum of considerable quality, and several of the reconstructed machines associated with signals exploitation work can be examined there. A small number of wartime communications receivers survive in private collections and in the collections of institutions such as the Science Museum in London and the Imperial War Museum. The valves have mostly gone dark, the coils have oxidized, but the circuits, if you could trace them on a schematic, still tell the story of what was achieved. Return then to that winter room in 1942, to the engineer, the wire, the smell of solder. He does not know what his device will be used for. The complete picture is deliberately hidden from him. Compartmentalization is the first principle of wartime intelligence, and no single person is permitted to see more of the picture than their role strictly requires. He knows only that the receiver must be more sensitive, must be more stable, must capture more of the signal and lose less of it in noise and drift, and the ordinary entropy of unshielded electronics operating in the damp English winter. He winds another coil, he solders another joint, he switches on the circuit, reaches for the tuning dial, and listens. What comes back through his headphones in that moment is not enemy traffic. It is static, the constant background hiss of the electromagnetic universe, a sound that fills the spectrum from the lowest frequencies to the highest, shapeless and meaningless and indifferent to the war being fought across it. But he knows, with the particular certainty that good engineers carry with them, that somewhere in that static the signals are there. German operators in their own huts, at their own sets, working their own keys, transmitting, giving themselves away. He adjusts the dial by a fraction of a degree. The static shifts, and somewhere in the shift, just barely, there is the ghost of a carrier wave. He reaches for his notebook. Britain's signals exploitation devices did not win the war. Nothing wins a war alone. But they gave British intelligence something that no amount of courage or calculation could substitute for. They gave it hearing. Not merely the capacity to detect that the enemy was speaking, but the ability to understand the shape of what was said, to identify who was saying it, to track where the speaker had been and guess where he was going. In a war fought as much in the invisible architecture of radio waves as in the mud and blood of physical terrain, that hearing was not a support capability. It was a weapon, quiet, precise, and almost entirely secret for 30 years after the guns fell silent. The wire mattered. The coil mattered. The engineer, whose name we may never know, mattered. They listened when listening seemed impossible, and the enemy never quite knew how much had been heard.